Just a few days ago, I talked about how Elon Musk's xAI broke the 30,000 GPU cluster limit and apparently will be able to do 50,000 or 100,000 or even, as Elon Musk might have joked, 1 billion GPUs in a coherent cluster. And I noted that sounds absolutely insane. And I suggested it was probably an innovation in Ethernet or TCP/IP or the stuff that runs your internet. In other words, how you're watching this video right now. And as it turned out, as I also thought was possible, it was Tesla that actually created the patents that I'm sure xAI is using. We don't have proof of that at this point. But anyway, Tesla published these patents back in February. Seti Park actually made note of these back in July, but I missed this entirely. And then he reposted the patents back on December 8th. And when I looked at that, I said, oh yeah, this is exactly how Tesla and xAI are doing this and how their gigantic Cortex and Colossus clusters are going to get through 50,000 GPUs, 100,000, possibly up to 1 billion GPUs, and still maintain coherence so they can operate as a single brain. So let's take a look. Hey y'all, it's Dr. Know-It-All. First of all, if you haven't seen my last episode, you should definitely check it out up here. You can watch it after this one or before, but the two of them are highly related to each other, so you should definitely watch both. Second of all, a huge thank you to Seti Park for putting this all out here, organizing it, actually explaining a lot of it. It helped me to understand the importance of these patents. So a really big thanks to Seti Park. Thank you so much for doing this. I'm going to go through several of his posts, but the first thing I'm going to do is just show the actual patent application itself. You can see it's dated 22nd February 2024. The important part down here is the abstract. We'll look at all the rest of this, over time during this episode, which will of course be very geeky, but I think it's also very important. Anyway, let's look at the abstract. The present disclosure relates to systems and methods for communicating in an Ethernet-based network using a transport layer without assistance of software control mechanisms. So that's the big innovation here, and we're going to talk much more detail about that in just a minute. In some embodiments, a first node is configured to open and close a link with a second node in the Ethernet-based network according to a state machine hardware of the first node. And again, note that the important part here is hardware, but also their state machine is quite elegant. We will look at that as well. The first node can include a hardware link timer configured to determine whether to replay the link, and that's the first of the supporting patents that goes along with this patent. And then the second of the supporting patents is the first node can include a hardware replay architecture configured to replay the link in hardware only. So the whole import of these three interrelated patents is to take something that used to be done in software and would take milliseconds or thousandths of a second and put that into hardware instead and reduce that latency to microseconds or millionths of a second. So 3 orders of magnitude faster by doing this one simple innovation. The interesting part about this, before we even continue on, the TLDR, is that everybody else, TCP/IP was developed 50 years ago, 60 years ago. It's the transport control protocol / internet protocol, right? So this was developed a long time ago, back in the days of ARPANET and things back in the 60s and 70s. And it's a really ingenious system that allows you to send information across lossy systems. So a lossy system, for example, is my Wi-Fi system that communicates with my router, that communicates with the internet, that communicates with your router, that communicates with your device, your laptop or your phone or whatever. Whether they're going through the air or through fiber cables or whatever it is, there is a very high degree of chance that a packet that gets sent, a little piece of information, will get lost or will arrive out of time with the other pieces of information. And there is software. There's very elegant software that's been developed a long time and is really, really robust. And, that's how this stuff works nowadays. Anyway, there's software out there that allows the systems to back off and to ask for these packets again and to receive the packets again, and therefore allows you to see things like videos or participate in Zoom calls or something when the internet is notoriously lossy. It loses tons and tons of packets. But of course, the consequence of doing this in software is that software has to run on hardware. It has to run on a CPU in this case, and the CPU is not designed only to run this particular thing. It does lots of things. It's a central processing unit. It maintains your system software. It runs your UI, and even on things like routers and so forth that don't have all of those other bells and whistles, it's really software that defines those routers. The software is a stack on top of the hardware, which tells it how to behave and allows the internet to work, but there's a lot of latency involved. And if you've ever had a really bad connection and tried to do like a Zoom call or a FaceTime call with that, and you get those really long delays and frozen videos and all that kind of stuff, you know exactly what I'm talking about. So that's where we started, and I think everyone was just like, yeah, this is what we'll do. But if we have a server cluster where we really need high speed bandwidth memory that can go back and forth between different nodes in, in a building or something, so it's relatively close by, we'll use a lossless system like InfiniBand, which doesn't have packet drops and everything, to have the interconnect. Now, number one, very, very expensive. Number two, it can get overwhelmed. If you have to guarantee that there is no loss in packets, there is a lot of overhead to make sure that works. And eventually, and apparently the number is around 25 or 30,000 GPUs. Around that number, if InfiniBand and other solutions get overwhelmed and you can't keep adding nodes, they can't communicate in real time with all of those other nodes at high speed. So of course, most people and most companies throw up their hands and say, well, what are we going to do about it? We have no idea. But of course, Elon Musk and his companies are famous for first principles thinking. They sat down, someone, Elon or somebody, sat down and said, is it physically possible to do this in a different way? Is it physically possible to transmit at very, very high speeds over a lossy transmission system? And then they said, yeah, the answer is yes, you can do that physically, right? With physics. Then the question becomes, how do you engineer this? And that's what these patents are all about. How do you engineer things to be 1,000 times faster than what you had in software? And the answer is you do it in hardware. Just no one had thought of doing that before. So here's figure number one, and look how darn simple this is. So more or less, these two figures are the same. We have figure 1A, which is the way things are done now, and you notice that almost everything is done in software except Ethernet frames and data encoding and stuff is done in hardware. So also notice you've got that same basic stuff going on down here with the physical specs, data encoding, VLAN, MAC address, Ethernet frames, etc. But notice that hardware now has eaten two other layers. It's eaten the IPv4 and 6 layer and the TCP UDP layer, replacing it with what's called Tesla Transport Protocol instead, which apparently is completely interoperable. You can take standard TCP software and run it directly on this. You just get a massive boost when you do that. So this is the difference right here. We've gone from using software for these layers to using hardware for these layers. Seems really simple in a figure, right? Very, very complicated to do. One other thing to notice is this top layer HTTP and Telnet and FTP, in other words, the transfer protocols, things going back and forth. Notice that in this case is replaced by PyTorch, which is the neural network programming architecture that pretty much everything is based on unless you're using TensorFlow. So you've got PyTorch at that top layer that's acting as a client that's running on top of all this other stuff. But the really big innovation is transferring TCP UDP over to TTP in hardware. So you're going from software to hardware, massive gains in that. That's just basically what they've done. But of course, we want to dig deeper, right? So we're going to dig deeper. So stick around. It gets even more interesting. This fundamental shift from software to hardware implementation, and by the way, this is Seti Park if you're just listening to this, addresses a critical need in modern AI training data centers where traditional software-based Ethernet implementations introduce unacceptable latency, and things like InfiniBand, other solutions that are lossless, get overwhelmed by the large number of cluster nodes. That's the other piece of this puzzle which no one could figure out how to solve. So as Seti Park says, the foundation of TTP, or Tesla Transport Protocol, is an elegant state machine implementation that manages network connections entirely in hardware. As illustrated in figure 2, the system uses 6 distinct states to manage link establishment and termination. So up here you've got closed state with no active connection. We've got an open receive sent state, intermediate states during connection and establishment, the open state where there's active connections going on, and then the closed receive sent states or intermediate states during connection termination. So if we start up here at the top, the connection is closed, right? This is between two nodes or something. What we get is an open sent. So the transmitting node sends a thing that says, please open. The receiving node says, yep, okay, I've got it opened. They open the connection, they do their things, they send their packets and stuff. Then we get a, hey, can I close this connection? And it says, yes, please close this connection. So again, super, super elegant and very simple and very easy to understand how this is working in theory. Much more difficult, of course, to implement this and engineer it. And so here we see how this state machine actually works in process here, right? So this is like time moving down from top to bottom. And we've got a connection between two nodes, one on the left, one on the right. The one on the left says, hey, open a connection. The one on the right says, yeah, it's open. It sends that back. Then you start sending information packets back and forth. So you send one, you send another, you receive the first one, you receive the second one, you acknowledge that you got those things and everything, right? So things are out of order. You send 1, 2, 3, and then you start receiving acknowledgement. I got number 1, I got number 2, I got number 3. So they're out of order. They're not, it's not waiting for the message to be acknowledge before it sends the next packet, it just goes ahead and sends it. So there's like a timeout window on the first side. On number one side, it just starts a timer. And remember, that second patent is all about a timer that's in hardware. So that hardware timer, it says, I just sent off packet number one. I'm going to count however many microseconds, let's just say it's 10 microseconds, to wait for acknowledgement that packet number one was received. But in the meantime, it goes ahead and sends packet number two over to node 2. So it's not waiting, it's sending the second one. Then notice it, oh, I got an acknowledgement for 1 that works. Then it gets an acknowledgement from 2 that it works. In the meantime, it sent off 3 and 4, gets an acknowledgement from packet 3, gets an acknowledgement from packet 4. Then it sends a close message. It's like, we're done. I don't have any more data to send you. And we get an acknowledgement for that. Number 1, we have not a 3 exchange open and close. There is 3 steps in the software version for each of these. So that shaves a step on each of these. But also what we've got is we've got this really, really fast transmission that's going on right here. But you're going like, well, wait, this is not a lossy situation. We haven't lost a packet. We haven't dropped anything. This right-hand one shows how that happens. So same beginning, it starts sending 1, 2, 3, 4, get acknowledgement of 1, 2, with 3, however, you can see here it says NAC or not acknowledge. It's like, didn't get packet 3, don't know what happened, didn't get it, whatever. At that point, it then has a replay loop. So again, that's that memory, that's patent number 3 we talked about. So remember, we're running a timer, waiting on this thing. If we get a not acknowledge, we resend it from our little memory buffer that we have. It's sitting there waiting, and it goes ahead and sends 3 again, then it sends 4 again. So it, even if it had sent 4 already, which it already had, it goes ahead and resends both of those to keep things in order. We get an acknowledgement of 3 and 4, and then we close the connection. And of course, another thing that could happen here is that we could get 1, 2 and get acknowledgements for those, and then the timer runs and it never sees an acknowledgement for 3. It just was never received, was lost someplace. So not a not acknowledgement, but just a complete timeout. Now, maybe what will happen with the receiving end is it will be waiting since there's no close, and it will eventually send a not acknowledge on its end as well. Don't know exactly how that works. Might be described in more detail somewhere down in the patent, but I haven't seen that. But anyway, after a certain amount of time, either node 1 is going to time out. And say, if it's 10 microseconds, it'll wait 10 microseconds. It'll go, never got an acknowledgement about packet number 3 from node 2, or node 2 will have a timer. It'll be like, I got packets 1 and 2. I'm waiting for packet number 3, waited 10 microseconds, never got anything, got packet 4. So I'm like, what happened? So it sends a not acknowledgement about packet 3, at which point that fires the replay from the hardware buffer that's storing those packets, very, very high speed RAM, so it can send that out quickly without too much delay. And so this is more or less replicating what's going on in software, but way, way faster. Now, the downside of doing this in hardware is it's not nearly as flexible. Software can basically, it can take a variable like, what is that timeout delay that I'm willing to wait? If it determines it's a bad connection, it can raise that from like 20 milliseconds to 200 or 300 milliseconds. So, like a third of a second, it can wait. And so it can back off and it can wait and take more latency as a hit in order to get those packets, because it's like, this is a bad connection. Hardware is not going to be able to do that. Number 1, because it's operating in microseconds instead of milliseconds. And number 2, because it's more limited in what it can do. It can't go backwards and resend packets out of order and stuff like that. I believe what it has to do is it has to go back to the one that was not acknowledged, and it has to start sending the packets in order from that point. So that means it's more limited, but the trade-off is with that limitation in flexibility, you get 1,000 times more speed. And we're not using this on the general internet. We will never have a hardware-based general internet solution. It will always be software-based, because the packet losses in Wi-Fi, over cable, over the internet, they're terrible. And so you need to have a very, very flexible system when you're dealing with a large internet. When you're dealing with an intranet for these clusters, in other words, they're sitting right next to each other like this. So they're not very far apart from each other. You have very, very high quality connections between them. You're not going to get a lot of packet loss. And when you get packet loss, it will be determined very, very rapidly, which means that in this case, hardware works well, whereas in the general purpose internet, it would be absolutely terrible. Then we have this figure that shows more detail of how the implementation is done. Previously, of course, these are just, abstract ideas. Here we're starting to get into how you actually implement this in hardware. And I'm going to let Seti Park speak speak about this since he knows a lot more than I do about this stuff. So the hardware implementation of TTP, or Tesla Transport Protocol, shown in Figure 4, represents a complete reimagining of network interface architecture. Key components include physical coding sublayer, or PCS, plus physical medium attachment, or PMA block, and then TTP medium access control, or MAC block, with integrated state machine, and dedicated transmit and receive paths optimized for low latency. So here you can see it passing information from, the receiving framework and the transmitting framework. It's sending information from this PCS plus PMA, which is obviously connected to the outside world. And I believe this is the clock, which might be the other patent, this 156.25 megahertz, I believe, clock, which is the thing that's keeping track of what's going on right here. So in other words, it can count to 156 million times per second. So it can do a lot, right? So we can get down to microsecond accuracy. It then sends things to static RAM over here that then goes to a system on a chip, which has some memory on it. All this is very, very high bandwidth. Then comes out from RDMA address encoding, goes back to the replay data path. This is the place where it can store that information, right? So it's going to send out things on the transmission, the TX framework. It's going to send things, but it's also going to store that for a small period of time. Again, it said it was only 256 kilobits. So this is a tiny little thing, not going to be able to store a lot of information, but it will store enough for that once in a while random packet lost. And that is, again, very, very fast memory that's just being cleared out as quickly as it gets acknowledgments from the receiving system. It's like, okay, I'm done with that packet. I got acknowledged. I can throw that one away, move the next one into the queue. So that's what this replay is doing. It's storing that data and replaying it if necessary, if it gets a not acknowledgement or if there's a timeout. And then we go back here, and this communicates with the rest of the world out there, the rest of the server cluster. And then we get a figure that shows the complete system integration. These are tiles like Dojo or NVIDIA GPUs or whatever. Goes through this NIP, these things, this high bandwidth memory here, goes through the Ethernet switch. I assume that this is a hardware-based Ethernet switch. I mean, that's the whole point of this thing. And then that goes out to CPUs, to DRAMs, to the NICs, all of that kind of stuff. So it's the communication between all of these individual nodes. So again, notice there's a lot of these, right? We've got one, up to tens of thousands, up to a billion or something of these connected together via Ethernet switches. And then they communicate with the slower storage, the network interface cards, all of that kind of stuff, the slower things on the outer world. All of these can communicate very quickly, and then they can pull from this other outside world as they need to get large amounts of data or something to go in for training. And the reason why all of this exists here is because Tesla's problem is very different than a large language model's problem. A large language model, a text token is like 2 bytes, right? So, the letter A or something like that is 2 bytes. Nothing. It costs nothing to have tens of thousands of these things. It's not bandwidth intensive at all to train large language models until you get to 25,000 GPUs that are trying to all do that simultaneously. Then it does get to be very bandwidth intensive. But for Tesla ingesting real world video, we're talking about gigabytes of data that have to be transmitted exceptionally quickly. And these things, if they're going to train, if you're going to split the weights of these neural network clusters across all of these different GPUs, you also have to have incredibly high bandwidth communication between the GPUs so they can share weight updates as each iteration of the training happens. So all of this stuff requires insane amounts of bandwidth, and obviously Tesla had to think differently about this than large language model trainers, and they came up with these patents in order to allow them to ingest this massive amount of bandwidth of data, and that just so happened to allow them to do intercommunication between the tiles, the different GPUs that they have internally, which then at least is a large part of how they're able to break the 25 or 30,000 GPU cluster barrier, and how they're able to go on to 50,000 or 100,000 or potentially a million or even a billion if Elon is not joking. So we're talking about a massive unlock that came about here, and it all came about from first principles thinking. And of course, from yesterday, we have Elon Musk responding to Zarathustra here. Zarathustra said, Elon Musk's XAI plans to expand its supercomputer to 1 million GPUs, and I have a feeling Tesla will probably do something similar to this. And then Elon said, nope, at least 1 billion GPUs. And I mean, again, He's got a laughing emoji there, but I don't know how unserious he is. That is a pretty crazy number. And of course, as Seti Park responded to this, Tesla may have cracked the code for maintaining coherence in massive scale AI clusters with partitioning and Ethernet as the key enablers. And so then the question is, why does this actually matter? Well, Seti Park and I actually, he was responding to me. So I appreciate the fact that he watched the video and learned something from me. But anyway, I'm learning from you as well, so thank you. But introducing coherence, the critical challenge in gigantic AI clusters. Yes, coherence is just like quantum entanglement coherence, or at least that's a good analogy. And so we have that here. So the problem with traditional architectures is in large-scale AI computing clusters, maintaining coherent operation between processing nodes becomes increasingly challenging as the system scales. While traditional distributed computing can function by dividing tasks and aggregating results, so that's okay, you can aggregate results, you pull them all back in again at the end, AI systems require coordinated interaction between processing nodes to enable effective learning and inference at scale. So in other words, they can't just go off and do their own thing and then push back the information when they're done, because you could be waiting, 10 seconds, which in the world of computers, high-speed computers, is an eternity. You're wasting 10 seconds waiting for the last data node to ship its information back. Heck, even if you're waiting a half a second at that point, it's an infinite amount of compute that you're wasting. It's huge amounts of petaflops that you're wasting by not getting all that data instantly and coherently. So that's the important part. You need all of this stuff to go in, train, come back out again, move around, all as one big giant block. Doesn't really happen very well with the current solutions. So then we have the statement of the problem. Traditional supercomputer clusters encounter significant limitations when scaled beyond tens of thousands of processing units, 25 or 30,000. These limitations manifest through increasing synchronization overhead, communication latency, and resource management complexity. At larger scales, traditional synchronization methods become progressively less efficient, leading to degraded system performance. Tesla's patents describe a systematic approach to addressing these scaling challenges through multiple technical innovations. Instead of attempting to synchronize all the nodes simultaneously, an approach that becomes increasingly challenging at scale, the system implements a partition-based architecture with coordinated timing offsets. And now it's time for a new word of the day. So, foundational innovation, Mesochronous computing. A Mesochronous network is a telecommunications network, or a data cluster, whose clocks run at the same frequency but with a constant phase shift. Compare this to a synchronous network. That would be where everything is locked together in the same amount of time. Here what you've got is the same frequency. The clocks are ticking at the same rate, but the phase is out. So if you think about a grandfather clock, right? You got tick tock like this. If you do something 180 degrees out of phase, if this one's up here, the other one's over here, and they cross and they cross and they cross. So just imagine millions of those things running at the same speed. They're ticking at the same speed, but they're all out of phase with each other. They can get out of phase. It's okay. That allows a lot more flexibility in a system like this than enforcing synchronicity. And of course, this has something to do with Tesla's patents, the one that I didn't go into so much about the clock. But the clock distribution system described in Tesla's patents implements Mesochronous computing with intentional timing offsets between nodes. This approach creates defined timing relationships between adjacent nodes while allowing controlled variations across the larger system. So basically, everything's a little out of phase from each other, and you get kind of a wave moving through the entire system. Kind of a beautiful solution to the problem. The timing offset system provides several technical advantages. Number one, distribution of computational activities across time, so that's cool, as well as across space. Number two, reduced simultaneous power demand, so each one's at a different part of the clock cycle doing different activities, so you kind of spread things out. Number three, support for system partitioning through natural timing boundaries. Skipping down a bit, and of course I will leave a link to this in the description so you can read it at more leisure because I'm not going through the figures and stuff. We want to talk about system architecture and organization, dynamic partition management, and then we have intelligent resource allocation, and then we have real-time monitoring and control. So in other words, it's able to see what's going on. And then we get to enabling technologies for coherent operation, including a global flag-based synchronization. So I love flags. I'm an old school programmer. So, I love to have binary flags that are true and false and things like that. So here we have the global flag system that provides efficient coordination between nodes, flexible synchronization mechanisms, and scalable communication patterns. We already talked about low latency communication. In other words, the fact that it's close by and you have these high quality switches. And then of course we have to have comprehensive error management because there's always going to be errors. That's the nature of the real world. That's the reason why there's packet loss in the first place. Otherwise everything would run perfectly. So we definitely need good error management to happen as well. And then finally we get to system integration and performance, where we get system architecture that demonstrates the characteristics of linear scaling throughout partitioning instead of exponential scaling. That's exactly where they get this massive increase in value. We get a scale that goes like this. Things become this much more complex rather than this much more complex as you add new nodes. We get reduced synchronization overhead, and then we get the very critical coherence maintenance at scale. The integrated system maintains coherent operation through coordinated timing relationships, efficient inter-partition communication, and balanced resource utilization. So all of this is done through multiple interrelated patents, but one of the ways each of these nodes can communicate with the other nodes nearby. Again, I don't think the point is that they're trying to be able to see the entire globe of things. That's what the phase shift in timing is doing. So they only need to communicate locally, almost like a convolutional neural network works. It just works on local areas. It only needs to know what's going on around it. At least that's my understanding of this, which enables each node to remain synchronized with the nodes around it. And those nodes are synchronized with the ones around it. And so what happens is you get this wave of synchronization that goes out from every single node, and that allows them to maintain more or less synchronization. They might not be perfectly clock synced, but they'll be within a deterministic time offset from that based on the phase shift of these clocks. So really, really cool stuff. And so Seti concludes here, Tesla's patents describe a comprehensive set of technologies that address fundamental challenges in large-scale AI computing. By combining mesosynchronous computing, dynamic partitioning, and advanced synchronization mechanisms, these innovations enable the construction and operation of AI clusters at previously unattainable scales. Again, we could be looking at an order of magnitude or more than anybody thought was possible before. The technological foundation established through Tesla's development of their Dojo system on wafer technology has led to these innovations in massive scale computing systems. This approach enables the operation of computing infrastructure at unprecedented scales. And by the way, I will throw in NVIDIA as well. NVIDIA has said that, in a way, they kind of said that Tesla saved their bacon by ordering so many of these chips at a time that other companies were like, we just can't handle anymore because we can't figure out how to synchronize all of them. Tesla was like, yeah, we'll take them. So they were able to synchronize all this stuff. So anyway, not just Dojo, but also NVIDIA. Anyway, this approach enables the operation of computing infrastructure at unprecedented scales, from current deployments of 100,000 GPUs to planned expansions reaching 1 million units. The synthesis of these innovations creates a framework for continued expansion of computing capabilities while maintaining system coherency at scale. This achievement represents a significant advance in large-scale AI computing infrastructure design and implementation. So yeah, folks, that's just some of the details available in these patents. And again, a huge thank you to Seti Park for explicating this. He is so good at this. If you don't follow Seti Park, please do. I think he very much deserves it. And while you're thinking about that, please do like and subscribe to this channel as well. I would love to make 100,000 subscribers by my 60th birthday at the end of January, and you can help me out. So thank you so much, and I'll see you in the next video. Bye-bye.